In the immense breadth of room among the endless stars glimmering in the evening sky, divine occasions of inconceivable scale and power occur, occasions that obscure whole systems and resound all through the universe. Today, we will dig into one such occasion, the heavenly calamity known as a cosmic explosion. From old civilizations that considered these occasions to be signs to present-day stargazers studying them to comprehend the universe, cosmic explosions have consistently entranced us. As of late, the star Betelgeuse has diminished decisively, leading a few researchers to speculate that it may soon transform into a cosmic explosion. If it happens, it would be the brightest cosmic explosion seen from Earth in more than 400 years. Today, we're going on a journey to understand these heavenly upheavals, their impact on our planet, and their account of our place in the universe. We delve into the captivating world of cosmic explosions. In the great theater of the universe, the stars are the protagonists. They are born, they live, and they die. But some stars give such a grand performance in their final act that it eclipses entire galaxies. They are cosmic explosions, the disastrous deaths of stars. But what is a cosmic explosion? Simply put, a cosmic explosion, or supernova, is a powerful and brilliant heavenly blast. It occurs during the final stages of a star's life when the nuclear fusion in its core can no longer support the star's outer layers. This causes the core to collapse under its own gravity, leading to a violent explosion that can momentarily outshine an entire galaxy. The energy released by a cosmic explosion is so immense, it's equivalent to the energy our sun would emit over its entire 10 billion-year lifetime. Cosmic explosions are not just captivating grand phenomena, they play a significant role in shaping the universe. They are responsible for the distribution of elements throughout space, elements essential for the formation of planets and life as we know it. In fact, it's believed that most elements heavier than iron, including gold and platinum, were formed by cosmic explosion blasts. So, the gold in your jewelry, the iron in your blood, and the calcium in your bones were once part of a star that ended in a grand explosion. Well before telescopes, space probes, and modern astronomy, ancient civilizations were already observing the stars. They saw patterns, mapped constellations, and recorded celestial events. Among these events were the sudden appearances of new stars, which we now know as cosmic explosions. One of the earliest recorded observations of a cosmic explosion was made by Chinese astronomers in 185 AD. They described a guest star that appeared in the sky, was visible in daylight for weeks, and vanished after about 8 months. We now know it was a cosmic explosion, and its remnants, known as RCW-86, have been observed with modern telescopes. Another famous historic cosmic explosion is SN 1054, the Crab Nebula, observed by Chinese and Arab astronomers in 1054. This guest star was about 4 times brighter than Venus and was visible during the day for 23 days. The remnants of this cosmic explosion, now called the Crab Nebula, are a vivid reminder of this celestial event. The ancient observations of cosmic explosions had a profound impact on how these civilizations understood the universe. They challenged the idea of an unchanging cosmos, a belief prevalent in many cultures. They were also used for astrological predictions and were often seen as signs. Today, we continue to study cosmic explosions, not as signs, but as opportunities to learn about the life cycle of stars, the creation of elements, and the history of our universe. Although our understanding of the cosmos has evolved, these celestial blasts continue to fascinate us with their power and mystery. Recently, the star Betelgeuse in the constellation Orion has drawn the attention of astronomers. Betelgeuse, a red supergiant nearing its dramatic end, began dimming significantly at the end of 2019. Some speculated it might soon become a cosmic explosion. However, it has since returned to its normal brightness. The most widely accepted explanation for this event is that the star emitted a massive dust cloud, which obscured some of its light and made it appear dimmer from our perspective on Earth. When the dust cloud dissipated, Betelgeuse's brightness returned to normal. This reminds us that the universe is not a static place but a realm where stars are born, live, and die in magnificent ways. Every star in the night sky has a story to tell, a story that begins long before we see its light. The life cycle of a star is a journey of transformation, from a mere cloud of gas and dust to a beacon of light that can outshine a galaxy. The journey begins in a nebula, a vast cloud of gas and dust. Within these cosmic nurseries, pockets of gas and dust begin to collapse under their own gravity. As they collapse, they heat up and form a protostar. Over thousands of years, the protostar continues to gather mass from the surrounding nebula. As it grows, the pressure and temperature in its core increase. When the core temperature reaches about 27 million degrees Fahrenheit, nuclear fusion begins. The protostar is now a main sequence star, much like our Sun. A star can remain on the main sequence, burning hydrogen in its core, for billions of years. However, eventually, the hydrogen fuel runs out. What happens next depends on the star's mass. For stars the size of our Sun, the core contracts and heats up, causing the outer layers. As a star grows, it eventually turns into a red giant. In the end, the core collapses, and the outer layers are ejected, forming a planetary nebula. This process leaves behind a white dwarf. However, as we travel through space, we find that not all stars meet their end in the same way. A star can also undergo a supernova. Its fate is largely determined by the mass and composition of the original star, while also having its own unique attributes. For instance, spectral analysis of Type 1 supernovae shows a lack of hydrogen lines. The most well-known subtype, Type Ia, occurs in a binary star system. A white dwarf, the dense remnant of a star like our Sun, accretes matter from its companion star. Once the white dwarf reaches a critical mass, it undergoes a nuclear explosion, resulting in a supernova. On the other hand, Type Ib and Type Ic supernovae are thought to result from the collapse of the cores of massive stars that have lost their outer layers of hydrogen, and for Type Ic, helium as well. Now let's focus on one of the most common types of supernovae we observe, Type 2. These supernovae originate from massive stars much larger than our Sun. Stars with at least 8 times the Sun's mass can undergo this dramatic transformation. Throughout their lives, these enormous stars are in a constant battle. Gravity pulls inward, while the force of nuclear fusion pushes outward. When a star exhausts its nuclear fuel, gravity wins the battle. The core of the star collapses under its immense gravity. This collapse happens incredibly quickly, in just a fraction of a second, and leads to a powerful explosion, a supernova. The outer layers of the star explode in a grand display, briefly outshining the entire galaxy. What's left of the star may form a dense neutron star or, if it was massive enough, a black hole. However, the legacy of the star lives on. The explosion scatters the elements formed during the star's life into space, seeding the universe with the building blocks for new stars, planets, and even life. When a star goes supernova, it's not just a light show, it's one of the most energetic events in the universe. The energy released in a supernova explosion is immense, equivalent to the energy the Sun emits over its entire 10 billion year lifetime. But where does this energy go? Most of it is carried away by neutrinos, tiny, nearly massless particles produced in vast quantities during a supernova. These neutrinos travel at nearly the speed of light, taking about 99% of the explosion's energy. The rest is released as light and other forms of electromagnetic radiation. This includes gamma rays, the most energetic form of light, and X-rays, which are less energetic but still far more powerful than visible light. The visible light from a supernova is so bright that it can briefly outshine the entire galaxy. This light can be seen across vast distances, making supernovae important cosmic beacons for astronomers. Although supernovae are rare to observe, they can also pose potential risks. The immense energy and radiation released in a supernova explosion can have significant consequences, especially if the supernova is close to Earth. One primary concern is the impact on our planet's ozone layer. The ozone layer acts as Earth's sunscreen, shielding life from harmful ultraviolet (UV) radiation from the Sun. However, an intense gamma-ray burst from a nearby supernova could destroy the ozone layer, increasing the amount of UV radiation reaching Earth's surface. This heightened UV radiation could have harmful effects on Earth's biosphere, leading to higher rates of skin cancer in humans and other animals and disrupting photosynthesis in plants, potentially affecting entire ecosystems. In addition to gamma rays, a supernova also emits a stream of high-energy cosmic rays. These particles can further damage the ozone layer and create cascades of secondary particles in Earth's atmosphere, increasing the radiation dose on the surface. In our exploration of the dangers posed by supernovae, there's another intriguing aspect to consider: gravitational waves. These are ripples in the fabric of spacetime caused by some of the most violent and energetic processes in the universe. Albert Einstein predicted the existence of gravitational waves in 1916 in his general theory of relativity. His calculations showed that massive, accelerating objects, like neutron stars or black holes orbiting each other, would warp spacetime, producing waves that radiate from the source. Supernovae, with their incredible mass and explosive energy, are prime candidates for creating such waves. When a massive star collapses and explodes, it produces a ripple effect in spacetime, allowing us to detect these cosmic events even across vast distances. Detonations, with the lopsidedness of their blasts, might possibly create gravitational waves undulating through space. These waves will be unimaginably feeble when they contact us and will represent no risk to Earth, yet they give us a new way to study the universe. Researchers have already begun detecting these waves with incredibly sensitive instruments, heralding a new era of gravitational wave astronomy. Fortunately, the likelihood of a cosmic explosion occurring close enough to affect Earth is tiny. However, understanding these potential risks is crucial, as it highlights our connection to the universe and how events occurring light years away can have consequences here on our home planet. As we've seen, supernova blasts are powerful events with far-reaching consequences. But did you ever guess that supernovae might have played a role in shaping Earth's history? Researchers have found evidence of past supernovae in the form of iron-60, a radioactive isotope present in ancient layers of Earth's crust and cores of Antarctic ice. Iron-60 is not naturally produced on Earth but is created in supernovae. Its presence suggests that our planet has been dusted with the remnants of these stellar explosions. One notable event is the Pliocene supernova, which occurred around 2.7 million years ago. Some scientists theorize that this supernova might have impacted Earth's climate during the Ice Age, potentially contributing to a period of cooling. There's also a hypothesis that supernovae may be linked to mass extinctions. The idea is that cosmic rays from nearby supernovae could damage the ozone layer, resulting in increased ultraviolet radiation on Earth's surface and harming life, especially shallow oceanic organisms. Although these theories are still being studied and debated, they underscore the potential impact of distant cosmic events on our home planet. It is a reminder that we are part of a dynamic and interconnected universe. As we gaze into space, we are looking not only at the past but also at the future. Stars will continue to be born, live, and die, and some will end their lives as supernovae. But what does the future hold for supernovae in our Milky Way galaxy? Astronomers estimate that a supernova occurs in the Milky Way on average about once every 50 years. However, most of these supernovae are not visible from Earth due to dust and gas obscuring the view. The last supernova visible to the naked eye in our galaxy occurred over 400 years ago and was observed by the famous astronomer Johannes Kepler. Rest assured, astronomers are keeping a close eye on potential supernova candidates. These include stars such as Betelgeuse in the constellation Orion and Eta Carinae in the constellation Carina. Both massive stars exhibit unusual behavior, leading astronomers to speculate that they could become supernovae in the relatively near future, on a galactic timescale. A recent study has shed new light on the mysterious behavior of Betelgeuse. This star, known for its semi-regular variations, has been the subject of intense scientific scrutiny. Betelgeuse's brightness fluctuates in a somewhat predictable but not entirely regular manner. Researchers have identified 4 distinct periods in these variations: 200, 420, 230, and 185 days. These periods correspond to the pulsation patterns of the star, particularly the fundamental mode and the first, second, and third overtones. This pulsation analysis, which accounts for the complex interaction between pulsation and convection, suggests that Betelgeuse is in the late stage of core carbon burning. The study also examines the so-called Great Dimming event, during which Betelgeuse's brightness significantly decreased from December 2019 to February 2020. Experts speculate that during this period, the star's effective temperature dropped by about 100 K, possibly resulting in a significant mass ejection. This event triggered a flurry of observations and analyses aimed at unraveling the mysteries of this distant star. The findings lead to an exciting conclusion. Betelgeuse could be the next star in the universe to go supernova. Given its current stage of late carbon burning, its high luminosity, and its complex variations, Betelgeuse is an excellent candidate for participating in this spectacular cosmic event. The study also notes that the star's high rotational rate as a red supergiant has sparked discussions about its evolution, including the possibility of past mergers with another star as a source of angular momentum. However, it is important to note that predicting precisely when a star will go supernova is extremely challenging, as it depends on many factors that are not fully understood. Even if a star shows signs of an imminent supernova, it could still be thousands or even millions of years before it actually occurs. Nevertheless, when it does happen, it will be a grand spectacle. The study of supernovae is crucial to our understanding of the universe. These stellar explosions are not only endpoints but also beginnings, enriching the universe with the elements necessary for new stars, planets, and possibly life. As we journey through the cosmos, we are constantly reminded of the grandeur and mystery of the universe. Supernovae are a testament to the life cycle of stars, the creation of elements, and the interconnectedness of the cosmos. We have studied their types, the risks they pose, their impact on Earth's history, and what the future might hold. These celestial events, as destructive as they are also creators. They seed the universe with the elements essential for new stars, planets, and perhaps life itself. Studying supernovae is not just about understanding these awe-inspiring events but also about grasping our place in the universe. They remind us that we are made of star stuff, that we are part of this vast, dynamic, and ever-evolving cosmos.